Hello everyone. Today we are going to analyze this simply supported beam. In this beam there is a concentrated movement M. It is acting in the clockwise direction and it is located at a distance of A from the left support. To find RA, let us take moment about B. In this case we have to follow right hand side rule. RA is acting in the clockwise direction, so it will be positive and the distance is L, so RA into L. The moment M is acting in the clockwise direction, so it is also positive. For RA, we will get a negative expression. That means our assumed direction is incorrect. We assumed RA to be acting upwards, but actually it is acting downwards, so we have to change the direction of RA. Here you can see that I have changed the direction of RA. By using this rule, we can find RB. RA is acting downwards, so it will be negative. RB is acting upwards, so it will be positive. For RB, we will get M upon L. Using the right hand side rule, we can find the shear force values at A. Shear force at just left of A will be 0, and at just right of A we have RA. It is acting downwards, so it will be negative. Using the left hand side rule, we can find the shear force in the point B. Shear force at just right of B will be 0. Shear force at just left of B will be RB. It is acting upwards, so it will be negative. Here you can see the shear force diagram. We know that in the simply supported ends, the moment will be 0. To find the moment in the point C, let us use right hand side rule. In the point C, there is a concentrated movement. So we have to find the moment at C 2 times, at just left of C and at just right of C. Let us find the moment at just left of C. RA is acting in the anticlockwise direction, so it will be negative and the distance is A. So we will get minus MA upon L. To find the moment at just right of C. With this, we have to add the concentrated movement. It is acting in the clockwise direction, so it will be positive. For these two, we can take LCM. We can take M outside. L minus A will be B. So we will get MB upon L. Alternatively, using the left hand side rule, we can easily find the moment at just right of C. RB is acting in the anticlockwise direction, so it will be positive and the distance is B. So we will get MB upon L. Here you can see the bending moment diagram. Using the Macaulay's method, we are going to make the expressions for the deflection and slope. For that we need to make sections. In this beam there are two different parts, AC and CB. So we have to make two sections. One in AC and one in CB. You can see that I have made two sections, one in AC and one in CB. Both of the sections I have made at a distance of X from the left support. Using the right hand side rule, we can find the moment about the sections. RA is acting in the anticlockwise direction, so it will be negative and the distance is X. The moment M is acting in the clockwise direction, so it will be positive. We know that with the concentrated movement, we should not multiply the distance. But here, we need to take this distance. This distance will be X minus A. In the power of X minus A, we have to apply 0. We know that when we apply the power 0 to any number, that will be equal to 1. So M into 1, it still will be M. We can equate the moment to EI d square y upon dx square. We have to integrate on both of the sides. When we integrate this, we will get this. To integrate x, we can use this formula. To integrate this, we can use this formula. When we integrate x, it will be x square upon 2. C1 is the constant. When we integrate this, we will get x minus a. One more time, we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x square, it will be x cube upon 3. Here there is no x, so we have to multiply with the x. C2 is the new constant. When we integrate this, we will get this. 2 into 3, it will be 6. In the point A, there is a vertical support. If there is vertical support, there will be no deflection. So when x is 0, the deflection y will be 0. We can apply these two in this equation. When we do that, we should not take these because this term is only applicable after the point C. Let us apply these in this one. This will be 0, this will be 0, this will be 0. So for C2, we will get 0. In the point B also, there is a vertical support. So when x is L, the deflection y will be 0. Now we have to take all of them. In this one, let us apply these three. We can take these two terms on the other side. L minus A will be B. For C1, we will get this. First, let us take the slope equation. In the slope equation, let us apply the expression for C1. Let us keep this equation as number 1. To find the slope in the point A, in this one, instead of x, we have to apply 0. When we do that, we should not take this. For the slope in the point A, we will get this. To find the slope in the point B, in this one, instead of x, we have to apply L. Now we have to take this also. We can eliminate this L and square so that we will get minus ml upon 2. Then we can take LCM. Let us keep 6L as the LCM. Instead of B, we can apply L minus A. Here we can use the formula A minus B the whole square. The formula is A square minus 2AB plus B square. Then we have to multiply with the minus 3 so that we will get this. Minus 3L square minus 3L square plus 6L square. We can eliminate. 6LA minus 6LA we can eliminate. L square minus 3A square is only remaining. So finally for theta B we will get this expression. Now we are going to find the location where the maximum deflection occurs. It occurs on the large segment AC. Slope will be 0 in the point where there is maximum deflection. We have to take this equation. We should not consider this because this term is only applicable after the point C. Let us take this and equate that to 0. We can take this term on the other side, so it will come as positive. We can eliminate M, L, 2 and here it will be 3. Finally for x we will get this expression. Now let us take the deflection equation. In the deflection equation, let us apply the values of C1 and C2. So that we will get this equation, let us keep this equation as number 2. Let us take only these because we are going to derive the expressions only between the points A to C. That is when x varies from 0 to A. We can take EA on the other side, it will come in the denominator. From these two, we can take M upon 6L outside. Let us find the maximum deflection. We can write x cube as x square into x. We have x square and x. We can apply that. And here for x, we can apply this. Root 3 we can take outside. We can write this as L square minus 3b square the whole power 1. And we can write this L square minus 3b square power 1 upon 2. We know the formula a power m into a power n is equal to a power m plus n. So L square minus 3b square the whole power 1 plus 1 by 2. We will get this. In the same way for these two terms we will get this. For these two terms we can take LCM. 3 minus 1 it will be 2. We can eliminate 2. Here it will be 3. So for the maximum deflection we will get this expression. To find the deflection under the concentrated movement. In this one, instead of x, we have to apply A. From these two, we can take A outside. We know that L is A plus B. So A plus B, the whole square will be A square plus 2AB plus B square. We can apply that. Then we can eliminate A square. B square minus 3B square will be minus 2B square. From these two, we can take 2b outside. We can eliminate 2 and here it will be 3. This is the expression to find the deflection under the concentrated movement. Alternatively, we can keep this expression also. Instead of b, we have to apply L minus a. And let us take this term a minus. Instead of b, we can apply L minus a. So a minus L plus a. So it will be 2a minus L. So there are two expressions. You can take whichever is easy for you. Now we are going to find the deflection in the center. In this one, instead of x, we have to apply L upon 2. X cube will be L upon 2 the whole power cube. We will get L cube upon 8. And x will be L upon 2. After the simplification, we will get this expression. Now let us see how to draw the elastic curve. We have just before made this expression. This is only applicable from the point A to the point C. That is when x varies from 0 to A. To find from B to C, we can use this expression. There are two changes. Here it is positive, but here it is negative. And instead of B, we have to apply A. So this expression is applicable from B to C. That is when x varies from 0 to B. For the maximum deflection, we have made this expression. When A is greater than L upon 2, when A is equal or less than 2, we need to use this expression. There are two changes. Here it is positive and here it is negative. Instead of B, we have to apply A. Now let us see some special cases. If the point movement is acting in the center, in these two expressions which we have made, instead of B and A, we have to apply L upon 2, so that we will get this. And to find the deflection in the center, in this one, instead of A, we have to apply L upon 2. To make it very simple, only in this one, instead of A, we can apply L upon 2. 2 will be eliminated, L minus L, it will be 0. 0 into this term, it will be 0. Now we are going to end this session. Thank you for watching this video.